In this video, we'll solve a physics problem about two electrons approaching each other. The problem states two electrons initially far apart are aimed directly at each other. Each has a speed of 1,000 meters per second. How close do they come before reversing direction and flying apart? Let's visualize this problem. We have two electrons traveling toward each other along the same line, each with a speed of 1,000 meters per second. Since electrons have the same negative charge, they will repel each other with an electrostatic force that gets stronger as they get closer. This force will slow them down until they stop momentarily at some minimum separation distance, and then they'll reverse direction and fly apart. Let's see what happens as these electrons approach each other. As they get closer, the repulsive force becomes stronger, slowing them down until they momentarily stop at some minimum distance. Our goal is to calculate this minimum distance. To solve this problem, we'll use the concept of relative motion and energy conservation. First, let's reduce this two-body problem to a single relative motion problem. For two identical particles of mass m with equal and opposite velocities, we can define a reduced mass mu as mu equals m times m divided by m plus m, which simplifies to m divided by 2. The relative velocity is the sum of the magnitudes of the two velocities. V relative equals v plus v, which is 2v. Step 2. Let's calculate the initial kinetic energy in the relative coordinate. The kinetic energy is 1/2 times the reduced mass times the square of the relative velocity. So that's 1/2 times m over 2 times the square of 2v. Simplifying, we get 1/2 times m over 2 times 4v squared, which equals m times v squared. Step 3. Now we need to determine the electrostatic potential energy at the closest approach. According to Coulomb's law, two charges E separated by distance have potential energy U equals 1/4 pi times epsilon naught times E squared over R. Since both particles are electrons with the same negative charge, they repel each other, creating a positive potential energy. Step 4. Now, we'll use energy conservation to find the minimum separation distance. Initially, when the electrons are very far apart, all the energy is kinetic, equal to m times v squared, as we calculated. At the closest approach, all the kinetic energy has been converted to potential energy, so the kinetic energy becomes 0, and all energy is now potential. By conservation of energy, we can write m times v squared equals 1/4 pi times epsilon naught times E squared over R minimum. Solving for R minimum, we get R minimum equals 1/4 pi times epsilon naught times E squared over m times v squared. Step 5. Now, let's plug in the numerical values to find our answer. We have the electron charge, E, is 1.602 times 10 to the negative 19 coulombs. The electron mass, M, is 9.109 times 10 to the negative 31 kilograms. The speed, V, is 1,000 meters per second. And the Coulomb constant, 1/4 pi times epsilon naught, is 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Plugging these values into our equation, R minimum equals 8.99 times 10 to the 9 times the square of 1.602 times 10 to the negative 19 divided by 9.109 times 10 to the negative 31 times the square of 10 to the 3. Computing this, we get our minimum approximately equals 2.53 times 10 to the negative 4 meters, or about 0.25 millimeters. So, to summarize our solution, 1. We reduced the problem to a single body with relative motion using the reduced mass. 2. We calculated the initial kinetic energy in the relative coordinate. 3. We determined the electrostatic potential energy at closest approach. 4. We applied energy conservation to find an expression for the minimum distance. 5. We plugged in the numerical values to get our final answer. Our final answer is that the electrons approach to within about 0.25 millimeters before reversing direction and flying apart. This problem illustrates an important physics concept, the conversion between kinetic and potential energy, and how electrostatic repulsion prevents the electrons from actually colliding.